as we continuously till, so this field has seen 40 years of fall plowing, moldboard plowing, which is full inversion, 100% burial of the residue. That's the most extreme tillage that we can impact the soil with. So fall plowing, and then spraying. In the spring, he dissed it twice. So he dissed it and then dissed it again to prepare the seed bed. This is on a research farm, Rogers Memorial Farm by Lincoln, and this is on a tillage study plot. It's the same field, and these two soils are literally touching. There's 2 strips, and then there's 6 of them. It's randomized replicated strips. So there's tillage, no-till, no-till with cover crops, tillage, tillage, no-till. They're just every other one across this field. Well, this is a pretty big difference to be right next door to each other in a field. But after 40 years of implementing that tillage study, this is what's accumulated and this is what's been depleted. And I can't iterate that enough. We're removing something from our soil when we farm. But if we implement these practices, we can accumulate that value as well, just doing and making the same or more profit. So it can be a valuable system if we implement it correctly. The other thing that we can do to speed that process up is apply manure. Manure and wood chips, they're made out of carbon and sugars and all sorts of compounds that have carbon in them and that are highly edible by the biology in the soil. And so that almost just jumpstarts the whole process by applying a ready-made food for the soil biology. It composts, it rots, it eats it, it cycles those nutrients and energy, and then it's right there in the soil system. So it's like drinking a pop. It gives you a quick boost of energy, little caffeine, and you can last out the rest of the class period, right? Not fall asleep. Just giving you a hard time, you weren't asleep. So the interesting thing is that these two soils start to function differently. When we deplete the resource, the soil stops doing what we think it should. So what are some of the things we think soil should do? I forgot to introduce my professional soil tech, Riley Hackbart. He just graduated from UNL with a soils degree, and he's here to help me set up, tear down. He's a soil specialist and knows a lot about soil, so he's going to help all day. And Riley, if you have a question, ask Riley when we're in the field or Augustin. I'm going to hand out this thing. It talks about what soil does for us. Right there on the bottom, it asks that question and then it gives you some soil functions. So soil provides a physical matrix, chemical and biological setting for water, nutrients, air, and heat exchange for living organisms. Whoa, it provides a habitat for plants to grow. That's easy to understand. We just talked about that. The next thing is it controls the distribution of rainfall or irrigation runoff, infiltration, storage, and deep drainage. So there's this thing called the water cycle. Have you ever heard of it? What's the water cycle? You guys know the parts of the water cycle? Let's start up here. We got a cloud. It rains. So that's precipitation. We get some precipitation on the ground. What does that water need to do to stay local? What's that? It collects. So where does it go?
To the low spot.
Yep, and where's that here? Where's the low spot here?
The river.
The river. What happens when it gets in the river? What?
Evaporates, maybe?
It could evaporate, but by and large, where do you think the majority of the river water goes?
Lakes. Down the river.
Down the river. Where does this river go? Do you guys know where your river goes?
The ocean. Big one.
What river is this? The Elkhorn River? Do you know where it confluences with the next river? At Fremont. Did you guys notice that Fremont got a big flood this year? It all came from right here. When you guys got that big rain in March on frozen soils. It all confluenced down there at Fremont where it joins the Platte River. Where does the Platte River go? To the Missouri at Plattsmouth. That's where it confluences with the Missouri. Did you know that this is the most days the Missouri River's ever been flooded? Out of bank flooding. They've maintained out of bank flow by releasing water from the series of dams that are all the way to Montana, down that river. They're releasing so much water that the river has stayed flooded out of bank for over 240 days now. That's the longest it's ever been out of bank. So that's pretty serious impacts of amount of rain accumulating to the low spot. Now where does the Missouri go? Do you guys know where it goes? And where's that confluence? Where does the Missouri meet the Mississippi? Some geography here. St. Louis. Right at St. Louis is where it confluences. And then where does the Mississippi go? To the Gulf. Where's that? What town's there? What state? Texas? That's a close guess. It's by the Gulf. No, it's Louisiana. And what's that famous town in Louisiana? New Orleans. New Orleans used to be closer to the ocean than it is. What's happening to the estuary there, or where that water's running into the Gulf? Do you guys know about that? Now the New Orleans is like 30 miles from the beach, and it used to be right on the coast. What happened? How did the land move? The town didn't get up and move. What happened?
More sediment deposited.
Sediment deposited there. Yeah, there's a huge sediment deposit, and all of the nutrients and things that go with the water are ending right there. Okay? So what happens in the Gulf of Mexico? Where's that water go?
The ocean.
Kind of nowhere, right? The ocean levels are not really rising. If we melt some glaciers, they think they might rise. But in general, it stays put. So that water's gotta go somewhere, otherwise we'd run out of water up here in the ocean, water would rise. So what's happening?
Evaporate.
Evaporation, thank you. Okay, so evaporation, condensation, precipitation. That's the water cycle, right? But what if we stop that and go back to where we started? It rains. What happens if that water doesn't make it to the river? Where would that water go locally? Rather than going non-local? Into the ground. What do you think that's called? When water moves into the soil? I just read it to you, and it's in clue number 2. Rainfall and irrigation runoff. We don't want it to run off to the river. Infiltration. So we're going to talk about the differences in these two soils and how the soil functions. So soil is integral to the water cycle. The water cycle can stay local. We can keep it right here in our county. Okay? Soil regulates biological activity, molecular exchange. It affects nutrient cycling. Nutrient cycling is what Augustine is talking about with manure for worth. If we can use manure in the nutrient cycle, get it to be eaten by a soil organism right here in our crop field, and then that soil organism gives it back to the plant, that's the nutrient cycle. We started with manure, it went into biology, it got shared back to the plant, and now it's into a crop, a grain that we're gonna harvest. And then the residue stays there, that nutrients return to the soil through composting, and it starts over again. So the nutrient cycle just goes in a circle. We remove the grain out of that cycle, and that's where depletion occurs. There's a small amount of depletion every time we remove grain. Every time that plant grows, it's not 100% efficient either. Some of that carbon is oxidized, lost in respiration. So plants don't just perform photosynthesis, do they? What do they do at night? They respire. So this is a plants class, right?
Yeah, they know
Okay.
that.
So, just checking. Respiration is producing CO2, whereas photosynthesis produces oxygen. And plants do both. And at nighttime, they produce CO2. So, it's not 100% efficient, the nutrient cycle. There's always losses in every cycle in nature. So, the last one, there's two more I want to cover, the functions of soil. Soil acts as a filter to protect the quality of water, air, and other resources. What happens when the rain is falling through the air and there's smog in the air? What happens to rain? What's produced when there's industrial waste in the air? smoke? You said it, acid rain. So what happens when if we suddenly had acid rain here in Pierce County and it fell on our soil, what would happen to that water and if it infiltrated? What would have to happen? That acid would be there. Would we just accumulate acid forever? No. The soil acts as a filter to filter water. So an organism would eat that acid. A bacteria would utilize it as food. And it would break it down into its simple elements and return it into the nutrient cycle. And so 90% of the filtering and nutrient cycle, 90% of that occurs because of biology. Something eats it. Physically, it's eating and pooping in the soil. That's what happens when it filters, buffers, and cycles nutrients. Or the thing dies, and then something else eats it. So that's just life, and that's what's happening in our soil. But it's really, really important to our water, air, and other resources so that our plant doesn't get that acid up into it and accumulate the acid or the elements, some pollution into the plant. It can just be eaten in the soil and reserved as soil organic matter. So that's where all those nutrients end up. So it acts as a filter. And the last one, this is the one I think that we all just naturally assume soil will do. It provides mechanical support for living organisms and structures. So when you drove to school today, did you think that the road was gonna move? What if it was just kind of washy, like on water? It'd be kind of difficult to drive on. We want our soil to stay put, don't we? And every day we think that road's not gonna move. Well, that's funny, because that's a function of soil that we just assume every day is gonna happen. Because soil's pretty stable when it's covered up and packed down and really dense, okay? So that's the simplest way that I can describe to you. But what do we look at a crop field? That soil's not moving, it's staying put. It's not blowing, we don't want it to blow away. We don't want it to go to the Gulf of Mexico. And we don't want our corn crop to just suddenly fall over, do we? We don't want it to blow over, we don't want it to wash away. We don't want it to just tip because it decided to get too lazy, okay? So soil provides support. That's the other function of soil. So I want you to hold on to those. I have a whole series of these. I'm gonna hand them out. Hopefully you can find some value in them and just document the functions of soil. Now I'm gonna talk about strictly the functions of soil related to water. So the water cycle, back to infiltration and storage. So these two are very different in color, and we know that came from management. That's the only difference between these two fields, these two pieces of the field. This is exarban soil. So every soil in Nebraska has a name and a number. And exarban is Nebraska spelled backwards. It's a really predominant soil in eastern Nebraska. It's widespread. And it's a heavier clay, silty clay loam. And at depth, there's a heavy clay underneath of it. So we're going to talk about that function with these monoliths. So when soil gets rain for the first time, that's called sorptivity. So the first wetting. And I'm going to show you what happens when this soil gets wet. So right now, this is called the soil aggregate. And these aggregates are like dirt clods that you throw at your cistern. Okay? And they hold together, don't they? They're not falling apart very easily. They're stable when dry. That's a dirt clod or a soil aggregate. So I'm going to talk a lot about aggregates and their stability. But really all I mean is how strong they are to remain a dirt clod. Okay? Now, they're stable when they're dry, just like Elmer's glue is stable when it's dry. It dries out and gets hard and it's stable. But what happens when it gets wet? Elmer's glue kind of soaks up the water. It can dissolve into the water, and it can release its hold, right? It can get unstable. So we're going to look at which one of these soil aggregates has stability when wet. This is called a aggregate stability test, or a slake test, S-L-A-K-E, slake. And slaking is the actual dislodging of a soil aggregate from itself. So when these little pieces of soil break apart, that's called slaking. It's a scientific term for break, okay? When water, so I don't know if you can see, there's a lot of air bubbles rushing out of the soil. Do you see those air bubbles coming out? That's when water needs to go in soil, it has to replace something. Air has to go out and water goes in. If there's no air in soil, there's no space for water to go in either. There's molecular space, but that's it. These air bubbles are in giant pores, big spaces inside that aggregate, and the water's rushing in and the air's rushing out. When the water goes in, water's real sticky. It wants to stick to itself. See how it's holding on the bottom of my finger? So it's real sticky. It binds to itself. It's got a strong chemical attraction. When it rushes into those spaces, it puts pressure on that space to bring more water in. It wants to fill the space with as much water as it can, and that pressure actually exerts against those soil particles outward. And when the water rushes in, we can test the strength of that bond, the soil stability. So this is called wet aggregate stability. Pretty simple, right? Took a little bit of explaining, but stable when wet. And we want our soil to remain stable when wet, and I'm going to show you why over here. This one, what's happening to it? So you can pretty quickly see what some of that carbon, the color, and these roots are offering the soil compared to when they're not present. And when we've taken them away for 40 years, not just 1 year, but 40 years of taking that resource away from this soil has changed its color, and it's changed its ability to stay stable when wet. And that's really critical. We boiled it down to the exact issue that causes our problems. Everything else is a symptom. So I'm sitting over here banging you on the head with a hammer, and somebody else walks over and gives you an ibuprofen. Is that going to help your head feel better? What's the real problem? The hammer, not your head hurting. You're just treating a symptom. You can remove the problem and then heal from me hitting you on the head with a hammer, right? So that's a really conceptually easier way to look at this. But we treat the symptoms a lot in farming. Our soil's moving, so we try and cover it up. We try and disc it up, we try and create ridges, we try and create terraces. We do a lot of management to keep the soil from moving when wet, so that it doesn't end up in the Gulf of Mexico. It's really simple. But this is what we're dealing with. 40 years of depletion, okay? So now, these are the same two soils in here. I guess I got it mixed up. I'm gonna turn these around so that they're right. The good soil's on the left. And these are already wet, these soils right here in these jars. So I've already wetted them, and they're the same two soils that I've showed you right here. So we've received one rain event on these. Let's pretend that, just like this morning, the soil's already wet. What happens, this has happened, the slaking's already happened in this jar, the soil's already moved, it's broken up, and that soil's settled to the bottom. So now this jar is full of this, and this jar is full of this, still up here, this one, okay? You can see the soil colors in there. They're the same two soil colors. Now we're going to see what happens when it rains one more time. After we've gone through this process, first wetting, now we're not in sorptivity, we're in wet infiltration. Saturated soils and their ability to infiltrate water is critical in farming. Now, here's my rain clouds. See the holes in the bottom? I'm going to put water in my rain clouds. We're going to condensate and precipitate right here. We're going to see if we can infiltrate. I'm putting in what's quantifiable to an inch of water on these soils in under 15 seconds. So that's about 240 inches per hour. So that's a really large rain event, okay? We can see 2, 3, 5, maybe 5 inches of rain in an hour. That'd be a lot. You'd be getting out your boats if that happened here. One night in Hebron, we saw 15 inches of rain, but it came in 6 rain events. It came in 12-hour period. So 15 inches in 12 hours, that's about 1 or 1.5 inches per hour. So you can see how we may get a lot of rain, but it doesn't come all at once. But when it comes all at once, this is what can happen. So pretty quickly, you guys can see what's going on here. The good soil on the left still has this structure. It's still sitting up here. It's still holding together. So those pore spaces that had air in them and the air rushed out, those pore spaces are still open. They're like a straw that's through the soil, and water can still run through that straw. This soil, the straw collapsed. It melted and it's on the bottom down here. There's no more holes in it. There's no more space in that soil. It's slaked and settled. It's deposited in the bottom. So it's deposited in the Gulf of Mexico, or at the end of your field, or in the terrace, or right in place. It doesn't even have to leave the field to deposit. It can just be right there. And it can be there. But check out what's happening in here. You see all that water? We're starting to get a little infiltration through some cracks that developed. Pretty soon those will seal shut too. And how long do you think water can sit on the top of your field before, if it's on a hill, before it runs off? Not very long, does it? It may be in that place for 1 second, or a half a second, before it's moving, already moving. It's on a hill. So, I can't, in this jug, we can see it stack up, but that doesn't actually happen. When it's raining, it's already moving. So we need it to go in the soil immediately. We need to have ready access to that soil. That's why this soil cover comes in so critical, because when it hits that and the drip runs around, that's time that it takes to run around and drip to the soil surface. So now we've just slowed down that process and allowed more time for the water to move through the system and then infiltrate. So just by having dead residue, we can slow down the actual time that the soil's on the land and make it last longer, stay in place longer. That's the goal. So I don't know what keeps track of my time. I don't know when I need to be done, but make sure that I don't run too long.
50 minutes, was that?
Yeah.
What time did we start?
Right about 9:30.
Okay. So we're at 45 right now? Okay. Well, we may have to try this to go faster. So I'm going to pour some more water in here, and then we're going to put this all together. And we're going to see what happens when it is on a hilltop. I cut these soils from the field, here on my right and your left. And these soils, make this a little more even. So you can see them. These are straight out of the field. They haven't changed. I didn't manipulate them. They're just as if I drove these cutters. They're sharp on the bottom. Drove them in with a hammer. And then I cut them off on the bottom and lifted them out. So this is an undisturbed sample. These I had to disturb to get them in the jars. These are undisturbed. So when it rains, it's about 240 inches per hour, so another big rain event. Then we're going to see what happens as it moves down the hill. So we're going to decrease the amount of time that it can stack. That's basically the concept. So real quickly, you can see the residue catching some of the raindrops, increasing the amount of time that the water's in place, and allowing it time to get on the soil surface and utilize those straw openings, the pores, like earthworm tunnels and all the biological space that's in that soil to soak water in. This soil has already slaked. It's done this. It's gone to the bottom. It's already sealed the surface with a crust from the raindrop hitting it. That impact actually compacts the soil on the top too. It pushes it down and it seals it. And where'd all the water end up? Right in the river. It's already down the hill and accumulating and going to the river. As soon as water's moving in a system, it's way harder for it to infiltrate. Just like the water in the river, most of that water goes downstream. It doesn't infiltrate, it doesn't evaporate because it's moving. So laterally moving is quicker than vertically or horizontally or vertically up and down. So where'd most of this water end up? 240 inches an hour, and most of it ended up in this aquifer down here. So this is clear full, and this came through the soil. What color is that water? Now that I stirred it up. But originally it was clear. I can see right through it. That just traveled through soil. Wouldn't you think it'd pick up some soil? Well, when it's stable, when those pores are stable when wet, the soil doesn't move. It doesn't detach and it doesn't relocate and it doesn't end up in the water. So our aquifer can be a lot cleaner. We can stop moving soil down through our profile, and the quicker that water moves through the profile with sediments, we move pollutants further and further into our soil, like nitrogen. We have a high nitrate issue in this area of the world, and a lot of that can occur because of water movement with soil. So we can get nutrients that are attached to things moving down into the profile past the root zone, and then they can start leaching, moving just with the water. It's not as if the faster we move the water through the system, the worse it gets. It's actually contrary to that. We don't want to move the things in the soil through the soil profile that accumulate nitrates at depth and then can move that even deeper. So this soil, or this water up here is running all over. We've got some paper towels here, Mr. Neal.
Oh,
No fear. You know what, Riley? It's all running out of here. I'm gonna leave this to you.
Alright, thanks.
We got a big problem. It's running all over.
It's not like we haven't done that.
Here you go. Have water and dirt must travel with paper towels. So we're gonna go over here and think about what we learned about stability of soil and the water cycle, infiltration, storage. We're gonna talk a little bit more about storage and root movement. So these two soils are the same soils that I just showed you. See these colors? These are dry colors, and the soil color changes when it gets wet. And what I've done here is glued this with Elmer's glue and water. I spray it, it gets wet, and the Elmer's glue seals it off. And so when that Elmer's glue affixes to the soil surface, it makes it show its wet color. So it changes the dry color of the soil. This is all dry, but it has a little bit darker appearance than this because it shows its wet color. This is the same two, no-till for 40 years, fall plowing, spring disking for 40 years. What are some of the differences that you can see in these soils other than the color? Roots? Where do you see roots?
No deeper down.
So down here in the bottom, some of these roots. So the neat thing about Exarban is it's got this topsoil, about 8 inches or 10 inches of topsoil. It's really similar to soils around here called Crofton, Nora Crofton. Have you heard of those soils? Those are really commonly farmed here. They're the heavier soil, not sandy. And they have topsoil. They have 6 or 8 inches of topsoil. It's that dark surface. So this is the topsoil right here. And in an Exarban, there's a heavy clay right down here. And clay has a lot more capacity to store water. And so all of our water storage occurs at depth in this soil, and the roots want to chase down and get that water. So when the roots can move, so can the water, and so can the air. And that's really important to understand. Root movement, air movement, water movement, it's all tied together. So do you see any roots down here in this soil? Not really. How about in this bed over here, or this monolith? See this big crack right here? There's a root that followed that crack down there. That's the only way it could get down, is after the soil already dried. How much root growth can occur when the soil is already dry? The plant's already suffering from loss of water, and it's trying to grow a root. It's not a really great time to grow roots. So the ability for this plant is depleted to grow its roots through the soil. What do you think of these layers right here? What do you think formed these? See this? It just comes apart. What happens when rain hits the soil? The raindrop impact, I said, pushes down on the soil. It created this compaction layer. This is called the surface crust. I'll just hand these all out so that I get them all out there. So, this one right here is the surface crusting. That's what I'm talking about. So it pounds down on the soil surface and creates this compaction layer, and it's right here. This is the surface crust, and it comes apart. You see how water doesn't want to jump across this void between my finger and this soil? It has surface tension, and so that drip will stay there for a long time. What would I have to do to get that drip to move and drip down here? What would I have to do? Anybody? Disturb it? Or could I add more water? So if I added more water above and it accumulated more, the weight of that water would make it cross this void, this space. So I've increased the amount of space that I'm showing you, but there's space between this layer and the next. And that space takes a lot of effort for the water to move across. Just the same way, it takes more water to get it to jump, to come out of the soil and go across that void. So every time there's a layer in the soil, it has to accumulate more water to go across it than it normally would. And that's called matrix potential. And I don't think that's mentioned in there, but matrix potential is really important when we have these layers in the field. And we'll look at it outside in the crop field. It's the ability for water to move through a matrix. Just like this paper towel has a grid or a fabric to it, a weaving, so there's actually a matrix, so to speak, and water can move through that matrix because it's continuous. This whole paper towel is wet, right? Not just part of it. If I got the bottom wet, the water would move up the paper towel. That's its ability to move through the matrix. The same thing happens in a soil, and that's called matrix potential. So its ability to wet the whole soil. What do you see down here below? So there's another layer right here. Do you see this curvy layer? What do you think created that curvy layer underground there? Any guesses? What tillage tool do we have that has curves on it? Rounded edges? A disc? Yep, every 6 inches or so, there's a disc blade moving through the soil. And it creates this curvy layer through the soil. I see that in a lot of crop fields. This is the first time I just kind of captured it on live. What's really cool is right down here, there's another really big horizontal fracture that you can't see. It's more on the back right here. See this horizontal fracture? That's from the plow. Plows move through the soil very flat, and it's like a sheet of paper down at the bottom depth. That's called the plow pan. We've probably heard of that as farmers. Plow pan. But this is a disc pan. And this is from field sweeps, from the trash kind of combs that are on the back of the tillage tools that smooth out the field. This compaction right here happens from that, and this one's from the rain. So this has a lot of problems, a lot of compaction in it. Plus, it's this soil, so it's not stable when it's wet. That's a big deal. So the ability for this to stay stable when wet is 0. We just saw that happen in those tests. And so once it's mud or pudding, it can't move water through the system. Plus the system needs more water to jump the matrix potentials, and air can't move through those gaps. There's no straws, there's no holes through this. I can show you in these beds over here an accumulation of holes. There's holes all through here, earthworm holes that accumulate in soil that's no-tilled. But this soil doesn't have holes in it. There's no accumulation of holes or straws. So there's no way for that water to move through the soil. Plus it's already melted because it doesn't have wet, stable aggregates. So we just have about 10 things that are against the soil from functioning, infiltrating water. And as soon as water stacks up on the land, we saw it. It runs off. Did you notice the color of that front water on that the tilled soil? It had some soil with it. So when we apply anhydrous, what does the nitrogen stick to that we put out there in the ground? Roots, maybe. What are you spraying it into? The soil, right? So it sticks to soil. So does phosphorus, primarily. Phosphorus sticks to soil really well, it binds to it. And when that soil moves, so does that nutrient. So when we lose our soil down to the river, we're losing nutrients. We need to capture that because the Gulf of Mexico has a lot of nutrients in it. A big problem. So this soil right here is stable when wet. It doesn't have horizontal fractures in it. And the roots can move through, soak in the water and soak in the air. So that's the main concept. You guys have any questions after that? That was kind of a big walkthrough to get back to this concept. The last thing I would say about this profile, this is called the soil profile. We're going to talk about that here coming up. But this layer right down here, do you see that brown layer on the bottom? Can you see that? On the bottom there, there's a kind of a tannish red soil. That's the B horizon in a soil. That's heavy clay. I talked about the heavy clay that's underneath this topsoil. I lined up the B horizons in these two soils the same. You see that line across there now that I pointed out? Right across there, there's a little bit of a color change, but they're not the same height. So the distance between that B horizon and the top is different. This one is pushed down. Plus, we've lost a lot of soil to the river. So as we erode soils and as we compact them, they become shorter and shorter and shorter. And so you can quickly see that compared to a fence line along a crop field. If the crop field's below the fence line, you know that soil has a problem. And it's shrunk. There's not as much air, there's not as much water, there's not as much space for roots and air and water movement. So this one's really tall. So I've got this soil profile card, and I wanted to build the soil profile with you all. There's 4 there that should be.
Should we get notices probably, or?
Yeah,
Right.
I'll finish this up real quick. I just wanted to conceptualize this, and I can speed up the outdoor process, but thank you for the idea, not to just put it down. And you can have a couple extras. So what I want you to do, this is double-sided tape right here. I want you to pick off one corner. It's kind of hard to pick off sometimes. The tape wants to come with the front of it, so just kind of get it with your fingernail. And then fold it down just a little bit. Don't tear it all the way off. Just fold it down to 12 inches. And then crease it right there, so it is just folded down at 12 inches. So what did I call this part of the soil right here? What's that called? The topsoil. Right. It's also got another name. It's right there next to the 0 mark. A. It's a horizon. So see the horizon right there, and then there's different horizons listed on this card. A, B, C. We're going to talk about those horizons and what they mean. So the A horizon in a soil is pretty dark. Do you see a dark colored soil in front of you? Take a pinch of that over the bowl and sprinkle it on your A horizon. And then once you get it accumulated on there, quite a bit of it, shake it back off into the bowl and put your soil back into the container. So why is the soil dark on the surface? What's up there? What's black? What we learned about? Carbon? Carbon. So there's an accumulation of carbon up here that came from living things. That came from plant roots, bugs, organisms like bacteria, fungus. And that all that life in the soil created death. And death is black. When it rots and composts, all the dead material ends up looking like black compost. And it sticks around in the soil. It's real sticky. So that's the A horizon. The next horizon is called the B horizon. And see this soil color down here? That red soil? You guys see the next color? Should be a tan or red. A little bit dark, but a little bit colored as well. Not the lightest soil. This darker gray soil is real typical in a Crofton soil that you might see around here, so that's kind of why I brought it. It's common to Nebraska. So we're gonna fold this down to maybe like 36 inches. So there's usually 2 or 3 feet of B horizon in a soil. And that's where the water impacts. So like I said, water moves through the soil and it takes soil with it, and it changes the color of that soil layer, and it changes its functionality. So go ahead, sprinkle some of that secondary gray color. You guys have a gray? Sorry, I didn't bring one over here. That's your B horizon color. So the B horizon does a lot of water storage. It does a lot of nutrient storage, and that's where the roots end up. So once the roots get past the A horizon and they need water and nutrients, they head to the B horizon. And that's where they end up. That's the stability of the soil. And we need the capacity for the roots, air, and water to get to that horizon. See what's preventing it from getting to that horizon here? All the layers that we created with our tillage tools prevent the roots and air and water from getting down to that layer, the B horizon. So now tear off your paper completely. You can use the next soil down. That's gonna be a more basic or primary color. The C horizon is made up of our parent material. So all of you kids came from parents. Somebody brought you into this world. Soil is brought forth from a parent material. And parent material is a basic color. It's not developed. It's original. It's the original copy. And everything else has been exposed to more and more life and nature, more and more of the elements. The B horizon, just a little bit of air and water and roots. The A horizon is where everything lives. It's like a bustling city. It's full of black smoke. That's how I like to think about it, is all this stuff that happens in a city ends up looking black. Well, that's the A horizon. And so you can kind of see the profiles as they line out there. You can go ahead and write a name on that if you have a pencil. You could write Crofton or Thurman. Those are some common soils around here. Thurman's a sandy soil, to be fair. But I just wanted to, you can call it your grandma's dog's name too, if you want. You can call it anything you want. But have you ever been to Crofton or Nora? Those are both towns in Nebraska, Crofton, Nora soils. And oftentimes we name soils after locations or vice versa. So.
What's the Nebraska state soil?
That's a good question.
You
You guys know the state soil in Nebraska? What's the state bird? Meadowlark. What's the state mammal? Mammoth? That's the state, whatever a mammoth bone is. Fossil. That's the state fossil. Couldn't think of the word. Our state mammal is a white-tailed deer. Yeah. Our state fish is the catfish, our state tree is the cottonwood, and our state soil is the Holdridge series. Holdridge, Nebraska, that's the most productive, predominant soil type that we have. The topsoil in a Holdridge soil is 36 inches deep. So there's 36 inches of life in a Holdridge soil before you get to the B horizon even. So it's a deep, dark soil. It's a mollisol, and it's really, really productive. A lot of water storage capacity. That's where all of our pivot irrigation centers there. So, okay, any questions or concerns? Mr. Neal, do you have any thoughts? Anything you want to clarify or?
I don't think so. I think this is awesome. We've read for our land judging competition, so, yeah, let's be as speedy as possible as far as getting boots and jackets and